Hello friends, today's question. A damped harmonic oscillator has a frequency of 5 oscillations per second. The amplitude drops to half its value for every 10 oscillations. The time it will take to drop 1/1000 of the original amplitude is close to. So we are given a harmonic oscillator, which is basically a damped oscillator, and the amplitude is dropping and the condition is given. It drops half to its original value after every 10 oscillations. So we can start by understanding that the decay factor per oscillation. So it is given to us that the amplitude drops to half its original after 10 oscillations. So we can say decay factor per oscillation. So we are given that after 10 oscillations the amplitude drops by half original value. Okay. So if we say that after 10 oscillations the amplitude becomes half the amplitude becomes half of its original amplitude, or you can call this as also initial amplitude. So it means that we can write this as A of 10 will be equal to A of 0 divided by 2, where A of 10 is the amplitude at 10th oscillations, or we can say after 10 oscillations. A of 10 is amplitude after 10 oscillations, and A0 is the initial amplitude. And the decay factor will be because of the exponential decay usually, and that is given as e raised to power b and multiply by n, where n is the number of oscillations. So we can write that the amplitude decays exponentially which is governed by the equation A of n is equal to A0 e raised to power minus b n, where an is the amplitude after n oscillation. An is amplitude after n oscillations, and b is the decay constant. So we can write this formula for n is equal to 10. For n is equal to 10, we get this as a of 10 is equal to a of naught e raised to power minus b multiplied by 10. And we already know that a of 10 is equal to a naught divided by 2. So therefore we get this as a naught divided by 2 is equal to a naught e raised to power minus 10b. A naught cancels out. So we get this as 1 by 2 e raised to power minus 10b. And taking natural log both sides, we can get natural log 1 by 2 is equal to minus 10b, which can be written as natural log of 2 is equal to minus 10b. Minus and minus cancels out. So we get b is equal to natural log of 2 divided by 10. This comes approximately equal to 0.0693. So we found out the value of the decay constant. Now we are going to come to the second part, the time it will take to drop to 1000 of its original amplitude. So we find out amplitude after time required, or we can say, let me write it here, amplitude after time required, or we can say time required when the amplitude drops to 1000 of the initial value, and initial value is a naught. You can say time required when amplitude drops to a naught upon 1000. So once again we are going to use the equation, this equation, and we are going to find out value of n, that the number of oscillations that are required for the particular condition. Okay, and particular condition is that when the amplitude drops to a naught divided by 1000. So once again we are going to use an is equal to a naught e raised to power minus bn, and here value of, you can say, n is 10,000, sorry, not 10,000 but 1000. Okay, so we can write an will be equal to a naught divided by 1000, and this becomes a naught e raised to power minus b n. Once again a naught and a naught cancels out, so we are left with 1 oblique 1000 is equal to e raised to power minus bn, and natural log both sides, we get ln upon 1 upon 1000 is equal to minus bn, and this becomes our minus ln 1000 is equal to minus bn, and minus goes away, and you can write this as 3 natural log of 10 is equal to bn, and 3 natural log of 10 is approximately equal to 6.907. So you can say bn is equal to 6.907. So we found out value of our bn, and b we just calculated is our 0.0693. So we substitute it here. B is our 0.0693. 0.0693 3 multiplied by n is equal to 6.907. So we can get that n is approximately equal to 100. So it means when the number of oscillation is 100, the required amplitude drops to A naught oblique 1000. So we are able to find out what will be the number of you can say oscillations. Therefore, the time required for 100 oscillations, time required for 100 oscillations. So here 100 oscillations basically means that the amplitude drops to A naught oblique 1000. So we found out the time required and we found out that n is equal to 100. So therefore time required for 100 oscillations, let us suppose that is given as small t, and small t will be equal to n multiplied by capital T, and here a capital T is a that is given that is equal to 1 upon f. So n is equal to 1 upon f. The frequency is given to us is 5 oscillations per second, and we found out n is 100. So this becomes 1.5. This goes away, becomes 20. Therefore we can say that t will be equal to 20 seconds. So this is the time for 100 oscillations, or we can say when the amplitude drops to A by 1000. So this is the time required for amplitude to drop to A naught oblique 1000. So the options that are available to us, you can see that option number A is the correct option. So you can say option A is correct. So this completes the question. Thank you.